Hi, welcome back to part 2 of a part 2 video for the final chapter of the Form 5 syllabus. In the previous video, we have covered half of the chapter, which includes the understanding of the nucleus atom, radioactive decay, and radioisotopes. If you haven't watched part 1 or still don't fully understand, please watch the first video, since this video will be continuing on the chapter with nuclear energy, management of radioactive substances, and ending off with a few past year questions. In a radioactive decay, transmutation is a process where one element changes into another. To compare, the mass of the daughter particles are less than that of the parent particle, and this difference in mass is called mass defect, or mass loss, where it is converted into energy. Due to this process, our beloved and genius Albert Einstein created a formula where it can be used to calculate the amount of nuclear energy released from the defect of the mass in a radioactive decay or nuclear reaction. This equation is E equals to mc squared. Another thing I should mention is atomic mass unit, which is used to measure the mass of the atomic particles. 1 AMU is equal to 1.66 times 10 to the negative 27 kilograms. Moving on, there are two types of nuclear processes, which are nuclear fission and nuclear fusion. Nuclear fission is a process of splitting a heavy nucleus into two lighter nuclei with the release of energy. Furthermore, if neutrons from the fission of uranium-235 continue to split with other nuclei and cause further fission, a chain reaction has occurred. Importantly, in order for a chain reaction to take place, a minimum of one neutron from each fission must trigger another fission. Or in other words, the mass of fission material must exceed a certain minimum mass known as the critical mass. Before we move on to the next nuclear process, nuclear fusion, let us look at the advantages and disadvantages of using nuclear fission. Okay, moving on to nuclear fusion, where two or more small and light nuclei combine to form a heavier nucleus and is accompanied by the release of a huge amount of energy. The one thing that differentiates the two processes is that fusion is much more difficult to achieve than fission because of how the hydrogen nuclei repel each other. Therefore, more energy is required to overcome the electrical repulsion between the nuclei. For example, the sun gets its energy from the fusion of hydrogen nuclei. Since nuclear fission is much easier to control, mankind has created something that can produce and harness this tremendous amount of energy, which is called the nuclear reactor. The way of generating power is that the energy liberated from the fission of nuclear fuel heats up the surrounding water. As a result, steam is generated to drive turbines, which in turn drives the electrical generators. As you can see in the systematic diagram of a nuclear reactor, there are several components that work coherently. There are the graphite moderator, uranium rod, control rod, coolant, thick concrete wall, steam generator, and turbine. We are almost there, so hold on as we are going to discuss on the proper management of radioactive substances. In a nuclear reactor, a very large amount of energy is produced from a very small amount of fuel. However, much of the waste is radioactive and therefore must be carefully managed as hazardous waste. Radioactive waste consists of a variety of materials that require different methods of management to protect people and the environment. Furthermore, there are three levels of waste. We have low, intermediate, and high-level waste, each with their own identification and ways for disposal. Next, we will talk about the negative effects of radioactive substances. Before we can talk about something sad, an interesting fact is that our bodies are always exposed to the external background radiation. The level of background radiation is very low and is not harmful to humans. To continue, besides death by overdosing in radiation, there are two major effects to humans, which are somatic and genetic effect. Somatic effect changes the appearance of the person exposed to radiation. The seriousness of the damage depends on the dose of radiation received. Symptoms include fatigue, nausea, hair loss, radiation burns, organ failure, and in worst-case scenarios, death. Genetic effect changes the gene pool by affecting the reproductive cells, which can lead to defective offspring in future generations of the exposed person. Symptoms include premature death, cancer in later life, and birth defects. With all of that, what can we do to ensure our safety when encountering these dangerous substances? One thing that we can do to ensure our safety is to get away from the source and let the professionals do the proper disposal. For those who are handling the radioactive substances, please follow these safety precautions. Read and follow the advice and instructions marked on the radioactive sources, equipment, and work manuals. Gloves must be worn anytime an unsealed source is being used or whenever contamination is likely to occur. Laboratory coats, long pants, and closed-toe footwear should be worn. Eating, drinking, applying cosmetics, or storing food is prohibited. When using radioactive liquids, plastic or metal trays should be utilized to contain potential spills. Before eating and drinking, wash hands and forearms thoroughly. Stronger radioactive sources should be handled with a robotic control system behind steel, concrete, lead, or thick glass panels. And with that, this is the end of the chapter and the entire syllabus for Form 5 Physics. Whoa! You did it! Congrats! Hope you understood this chapter and get flying colors for your upcoming tests and finals. Good luck! Wait! Before we end our video, please stay with us for a moment to try your very best on answering a few past year questions. Please pause the video to try this yourself. And this is the solution. Hope you did well. Goodbye! The background radiation is due to cosmic radiation from space and radiation from small amounts of radioactive substances present in rocks beneath the surface of the Earth. The half-life of a radioactive nuclide is the time taken for the activity of any given sample to half of its original value. T equals 1/8 minutes when the activity is equal to 400 counts per minute, and T equals 5/8 minutes when the activity equals 200 counts per minute. Therefore, the half-life is equal to 5/8 minus 1/8, which is 4/8, which is half a minute. A spark counter cannot detect beta particles due to its low ionizing power. Thus, no sparks are produced when a beta source is placed 1 centimeter on top of the gauze. On the contrary, alpha sources have high ionizing power. When an alpha source is placed close enough to the gauze, the alpha particles emitted by the source will ionize the air between the cathode and the anode. Since the potential difference between the cathode and the anode is very high, the positive ions will be accelerated to the cathode at a tremendous speed. At the same time, the negative ions will be accelerated to the anode. The movement of the ions across the air at such a high speed will cause sparks to be produced, and thus can be seen if the experiment is carried out in the dark. The sudden expansion of the air due to the movements of the ions will cause sparkling sounds to be heard. If the alpha source is raised to about 10 centimeters above the gauze, the sparkling will stop. This is due to the fact that alpha particles have a range of only about 5 centimeters in the air, and thus will not be able to reach the counter. The nucleon number remains unchanged, but the proton number will be increased to 7. The daughter nuclide is 714N, which is a nuclide of nitrogen. No, since beta particles are electrons, which have negligible mass.